Welcome! This lecture concerns the notion of cuts. Here, we deviate in our presentation ever so slightly from that of your textbook. We first define a cut. Given a set of numbers S, a cut is a decomposition of S into two subsets SL and SU, satisfying two properties. First, the union of SL and SU account for all the points. Their union equals S. Second, every element in SL is strictly less than any element of SU, and every element of SU is strictly bigger than any element of SL. In other words, SL is to the left of SU on the number line. Here, the subscripts U stand for upper and L stand for lower. Here are some examples of cuts. First, we cut the natural numbers to the set of numbers less than or equal to 5 and the set bigger than or equal to 6. Notice that these two sets account for all natural numbers. The same two sets do not form a cut of the integers because while one set remains to the left of the other, the negative numbers are not present in either of the sets. The set of integers less than -1 and the set of integers greater than 0 do not form a cut of integers because the numbers -1 and 0 are not represented. The set of all rational numbers less than -2 and the set of all rational numbers greater than or equal to -2 form a cut of the rationals. We will use this concept to capture what we expect of the continuum of the real number line. Imagine the set S being like a piece of string. A cut separates it into two halves by first picking a point, which may or may not be in S, and separating the string at that point. The left half we will call SL, and the right half we call SU. If the point at which we perform the cut was originally an element of our string S, then it would end up either as the left endpoint of SU, making it the minimum of SU, or the right endpoint of SL, making it the maximum of SL. And if the string S has to start with no sizable gaps between its points, then the other half should have elements that get right up to the cut. So if the cut point is stuck with the right half, the left half should have a frayed end with no maximum. And if the cut point is stuck with the left half, the right half should have a frayed end with no maximum. So if we understand the continuum to be a set where all the points are present and accounted for, and one where there are no sizable gaps between points, then we would expect a cut of the continuum to leave us with exactly one half with the endpoint and the other half with a frayed end. Notice that this is exactly what you've learned about the real number line. If you divide the real number line at a point P, then one half will have a closed bracket, making it include P, and the other half will have an open bracket, making it exclude P. If the cut leaves you with two pieces both having the endpoints, then there must originally be a gap. If the cut leaves you with two pieces, neither of which have the endpoints, then the point chosen to cut from must have been missing from the original set. With this intuition, we will define the notion of order completeness. We say that a set of numbers S is order complete if, for any cut with a lower half SL and an upper half SU, either SU contains a minimum, or SL contains a maximum, or both. Now, in the intuition on the previous slides, we talked about how for a continuum, we expect exactly one out of the two sets to contain an endpoint, but not both. But recall that the situation of both having an endpoint describes there being a gap between the numbers, not that there is a missing number. We want the concept of completeness to capture only whether there would be a missing numbers or not. The fact that there are no gaps, we can capture using the fact that the real numbers contain the rationals as a subset, and we already know that the rationals have no gaps. So we have a division of labor. Completeness only concerns whether numbers that should be there are missing or not. We next talk about a property of order-complete sets. Proposition: let S be a set of numbers and assume it is order-complete. Then, for any non-empty subset T that is bounded above, the set SU of all upper bounds of T has a minimum. The conclusion portion of this proposition, that is, the part that comes after the word then, is also called the least upper bound property. So our proposition says that any order-complete set satisfies the least upper bound property. In fact, the least upper bound property is logically equivalent to our definition of order completeness. That is, if you assume a set S satisfies the least upper bound property, then you can prove that any cut of S into SL and SU will be such that either SL has an upper bound or SU has a lower bound, or both. So, in an exposition, one can choose either statement as the defining statement for order completeness. I chose the statement I chose because I feel it is intuitively more obvious that the definition has something to do with missing numbers. In your textbook, the least upper bound property is taken to be the definition of order completeness. The difference is only that of storytelling and not of mathematical content. Let's give a proof of this proposition. We will divide the proof into two parts. First, we consider the case where T is finite. I note that in this case, to prove the least upper bound property holds, we do not need to invoke completeness. Second, we consider the case where T has at least two elements. Note that the two cases have significant overlap. The only case not in case 2 is when T has only one element. It is technically enough to study for the second case only situations where T is infinite. I am proving it all the way down to two elements for pedagogical purposes. The proof should make it apparent why it doesn't work for sets with only a single element and why we must separately consider two cases. Let's first treat the easier case where T is finite. Step 1. T has a maximum. This follows from proposition 12 on the usable statements sheet, where we proved earlier this week that any finite set has a maximum. Step 2. The maximum of T is an upper bound. This follows from proposition 15 on the usable statements sheet, as we proved earlier this week that the maximum of a set is automatically an upper bound. Step 3. Any upper bound is bigger. We notice that any upper bound of T must be at least as large as any single element of T. And since the maximum of T is by definition an element of T, it must be smaller than or equal to any upper bound. Based on what we've done already, we can conclude that this element max T must be the minimum of SU. As max T is an upper bound, it is an element of SU, and since any other upper bound is bigger, max T is the minimum or least upper bound. The next several slides will concern the harder case where T has at least two elements and can potentially be infinite. We will need to use the completeness condition, and to do so, we need to build a cut. Our cut will keep SU as is and define SL to be anything in S that is not in SU. We can check that this is indeed a cut. First, SL is not empty. Since T has at least two elements, it has at least one element that is less than some other element of T, disqualifying it from being an upper bound. This element then must belong to SL. Next, SU is not empty. By assumption, T is bounded above, which requires T to have an upper bound, which would become an element of SU. That SL union SU is the whole of S is by definition. Finally, we need to check that elements of SL are less than elements of SU. We can argue by contradiction. Suppose there is some element S in SL that is not less than some other element T of SU. By transitivity, S bigger than T and T bigger than any element of big T means that S must now also be an upper bound of big T, which would mean S is not in fact an element in SL, but an element of SU, and this gives a contradiction. So we have proven that with this choice of SU and SL, we've made a cut of S. Now we can try to apply the order completeness property to our cut. This says that either SU has a minimum or SL has a maximum. If SU has a minimum, then as this is exactly what we hope to prove, we will be done. So we only need to worry about the case where SU does not have a minimum, and by extension, SL has a maximum. I will claim that this cannot in fact happen. On the next slide, we prove this is so by contradiction. Suppose for contradiction that SU has no minimum. Then SL has a maximum, which we call S0. This is using the order completeness. Then there exists some T0 in T that is bigger than S0. For if not, S0 will be an upper bound of T and be in SU, but we know that S0 is in SL instead. I claim that no other element of big T can be bigger than S0. We again argue by contradiction. If there were two elements of big T that are bigger than S0, one of them has to be smaller. The smaller one cannot be an upper bound of T, so it belongs to SL. But by assumption, the smaller one is also bigger than S0, contradicting our knowledge that S0 is the max of SL. This was the most complicated step of this proof. I invite you to pause the video here and think over exactly what just happened. From here on out, this is smooth sailing. By transitivity, since except for T0, which is bigger than S0, all other elements of big T is smaller than S0, by transitivity, we know that T0 is at least as large as any element of T, and hence is its maximum and an upper bound. But since T0 is the maximum of T, and hence an element of T, any other upper bound has to be at least as big, forcing T0 to in fact be the least upper bound. And hence SU in fact has a minimum, and it is T0. This completes our proof. This was a longer and more abstract lecture than the previous ones, so let me give a quick summary. First, we defined today the notion of cuts and discuss how it intuitively relates to the idea of completeness, specifically about missing points. Second, we defined formally the notion of order completeness in the language of cuts. Third, we showed that order complete sets possess the least upper bound property, that if T is a non-empty subset with an upper bound, then the set of all upper bounds of T have a minimum. While I think the definition of completeness using cuts is more intuitive, the least upper bound property turns out to be easier to wield when applying this idea to understand the real number line. We will more frequently invoke the least upper bound property when the completeness of the real numbers will come into play, and only very rarely, if ever, get our hands dirty and use the definition in terms of cuts. This is actually a common theme in a lot of mathematics, that the intuitively obvious definition is not the easiest to use, and that the easiest to use definition is not intuitively obvious. Most textbooks in most fields tend to streamline the presentation towards the easier to use definitions, frequently omitting the explanation of the intuition behind the definition. When you read mathematical texts in the future, you should always ask yourself, why the definitions are taken that way. Building up a good mental intuition about the definition is the only way you can actually understand mathematics. Okay, that's it for this lecture. See you next time.